did not formally tell you what the limit rules are.
Yeah.
I used them rather informally when I was doing these processes, which is not a big deal. They are used pretty informally. The idea is that if you have a sum or a difference or a product or a quotient, then basically the idea is if all of these things exist already, then you can just plug it in. And we did a lot of plugging in when we were computing our limits, right?
Yeah.
Except for polynomials, it certainly is just plugging in, right?
Yeah.
But it goes even beyond that. As long as all the limits of each of the pieces, individual pieces exist, then the limit of the whole thing exists, and you can just plug in the number into the parts.
So plug it in, and I'll get 14 divided by. Wait. 14 divided by 18, right?
Yeah, and you reduce that, and that should be your answer.
Yeah.
Correct.
So it'd be 7 over 9.
Yeah. So the only thing to be wary of is that's because all the limits existed and the bottom was not heading towards 0. There was no fatal flaws in the calculation, right? So you're able to just plug it in. That's because this function, however complicated it is completely defined and continuous around 9. So you can just plug it in like a polynomial. Like a polynomial is continuous and well defined around every single point.
Yep.
So that's why it feels like it is a plug-in chug. I don't want you to think every single limit is a plug-in chug. Right? You saw the techniques we did before with the conjugate and these other algebraic things to do first.
Yep.
So don't get lured into thinking I always just plug it straight in. That's the only thing. But certainly if the numbers are working out well, you should be able to just plug them in, and that's what the limit laws are allowing you to do.
Okay.
Yeah.
I have to push back again.
Why do you need to go? Why do you want to stick around?
I should yeah. It's not because it's anything infinity, it's for different reasons. Yeah, it's just not interesting. I can take that. Question? Find a given limit. So CSUM, the second one, is certainly a plug and chug.
Yep.
That's a polynomial, right?
Yeah.
Have you seen a polynomial? Just plug it right in. So whatever it is.
Let's see what we got.
Now this one though, number 3.
Yep.
So now I said, with conjugate, if you see a root somewhere, it's a good hint that you want to use the conjugate technique. So in this case, it's switched up. It's switched up this time. The radical is in the denominator, but it's the same scheme. You're going to multiply by root 5h plus 1 minus 1 above and below.
Yep.
And see how that all works out. That makes sense?
Yeah.
Is that okay?
Okay. So that means we're just gonna plug in h as 0.
Actually, hold on a second.
And then we're
See, I got
left.
ahead of myself. Look. It's actually okay to plug it in, right?
So just plug h in as 0, and then we're left with like 5 divided by 2.
Yeah. So you didn't have to do I lied. You didn't do conjugate. Because the bottom, see, I forgot what I told you guys. Check C has towards 0, right? The bottom's not heading towards 0, so there's no reason to even go for the conjugate. This one is a plug-in chug. You just plug it right in. Because the bottom's fine.
Yeah.
See, I see certain forms. I think it has to be that thing. Always check first. Wait. Oh, yeah. You may have these highlights in some cases. It may be absolutely necessary to have in some cases. I'm going to approach everything. I really do have to approach assuming they could answer your question, like you saw some, maybe 20.99. It's going to take a long time to figure out what 0.99 is that first. And that's a lot of computations and the brain. So it's going to be more efficient to have to do those kinds of things. Same one. Yes. You would be disadvantaged. Have a good evening. All right. If you have any questions, just ask them now. I'll stay around for 2 minutes if you need. Office hours between 5 and 6 in this classroom.
You know something wrong.
You have a calculator?
Left it at home.
Oh, yeah.
So they make money off it. They have to make money off it.
Number 9.
Come on, Lee. What do you say?
Number 9.
9. Is the statement is true for all x less than, or sorry, not equal to 0? So let's see.
Yep.
X sine sin on x. So first of all, this portion here, you should always know that sine, not just sine, but cosine, of anything, no matter what's inside them at all, no matter whatever's inside. However complicated this argument comes, always between -1 and 1.
Right.
Every sine and cos value is trapped in -1 and 1. Sine and cos cannot be any larger than that, or any smaller than that, right? So now, if I were to take this expression, right? So, like I said, the argument could be anything. This could be 10 on x, and cos, the same thing. 10 on x, that would be true, right? This would still hold, just matter what's inside.
Yep.
And if I multiply the whole thing by x,
Yep.
the same result should still hold. Except, if I multiply through by x, what if x is negative? Then it would switch these signs. This would be a positive, and this would be a negative, and inequalities would make no sense anymore. I couldn't have a positive less than a negative. So what they're trying to say with these absolute values is really I'm just multiplying the whole thing by x to make sure these signs stay the same. They're multiplying the endpoint here by absolute value x. So it is true. If I multiply 1 or -1 by absolute value x, the inside just by x, because the inside, this function, it doesn't matter if I change it to negative and positive. This is still the lowest bound it's ever going to have. It doesn't matter if I change the sign here. And then over here, I multiply 1 by the absolute value of x, not just